So what I'm going to present today is kind of a mashup of a series of talks. I'm going to move quickly. If you want more information, the details can be found in these and other papers. Some of them are online. Others, if you just send me an email, I'll get you a copy of the paper. So one of the big discoveries in the last 40 years or so is that most of the seafloor is hydrogeologically active. Pretty much anywhere you look, there is water moving in and out of the seafloor, sometimes at low rates, but geologically at fast enough rates to matter in terms of the chemistry of the materials in the substrate in the seafloor itself or in the ocean. And that hydrogeologic activity has profound influences. We've heard about some of them already, but it really does control the chemical evolution of the upper ocean crust, and also, of course, over geologic time, the chemistry of the oceans. And lately, of course, there's been a lot of interest in in microbial life. And a subset of hydrogeology in the seafloor is known as hydrothermal circulation, and that's the passage of fluids through the rock driven by heating of some kind. In fact, there's really a diverse array of hydrothermal styles found on the Earth, and I'm not sure we're done with these yet. I think there's probably other mixtures and styles that we're not necessarily aware of. At the high temperature end, you've got those that are magmatically driven primarily or one step removed by cooling of hot rock. You've got serpentinized systems. If they're largely exothermic in their heat origin, they're somewhat lower temperatures. And then you've got these sort of background flow systems that are essentially driven by lithospheric heating or some internal heat supply that's modest but everywhere. And in fact, those are what I'm going to focus on today. It's where I've done more work, but also because I think they're relevant to some of the characteristics we might need to look for when we think about ocean worlds. And they create some challenges for us. This is a table I pulled from an intro hydro textbook, except I inserted the ocean because they always leave it out. And if you look at the different reservoirs for free water on and near Earth's surface, the upper ocean crust, just the porosity in the volcanic rock alone, gives you a volume commensurate with all the ice sheets and glaciers on the planet. So it's certainly worth considering it as a major hydrologic store. And you might say, well, that's salt water. Well, guess what? So is the groundwater. The vast majority of groundwater is brine. And so, in fact, it's been included. People have just kind of ignored that ocean reservoir. We heard earlier about the heat loss of the Earth. It is about, give or take, 80 milliwatts per meter squared. It turns out, coincidentally, it's about the same on the continents as it is in the ocean. Turns out that is just a coincidence, most likely. The total heat output of the planet, it's about 40 trillion watts, and it's equivalent to having one of these festive Christmas lights for every square meter of the planet, which is something we probably should think about in the future. Now, if you look at, though, the heat flow through the oceans, there's this trend that's been seen and known about for about 30 years, going on 40 years now. And that is, here are heat flow measurements, conductive heat flow measured in the ocean, and they're binned in 2 million year bins, thousands of data points, from zero out to about the oldest seafloor, Jurassic seafloor. The red squares are means, the bars are plus or minus 1 standard deviation, and the curves, the dashed curves, are standard lithospheric cooling curves. There are other curves, but they all look about the same. And what you see here is that the mean values that are measured are lower than these curves. You can express the same data this way by calculating the heat flow fraction. It's the fraction of the lithospheric heat that's actually represented in the conductive heat flow measurements. And so these curves show the same thing. And when you get to about 60 to 70 million years, with some scatter, they coincide. And this gap is known as the global heat flow deficit. If you plot it conceptually, it's shown here, and here it is for the heat flow fraction. And about 30% of the deficit could be attributed maybe to seafloor spreading conditions. Although that's probably generous, but at least 70% is on the ridge flanks. That is, it's on the parts of the seafloor that are virtually unaffected by the direct seafloor spreading processes themselves. And that's circulation that's occurring at a much lower temperature on average. Well, if you know the amount of heat that's being extracted, and it's about a quarter of the Earth's heat, okay, that's missing in our heat flow surveys. And then you make some estimates of the temperature of the fluid, you can calculate the flow rate. And what we find is that on the ridge axis, the flow rate of hydrothermal fluid is around 40 cubic kilometers per year, which interestingly is the same as the rate of crustal production. Thus, perhaps the canonical 1-to-1 water-to-rock ratio that was detected years ago in rocks that have undergone high temperature alteration. On the other hand, if you look at ridge flanks, it's at least as high as the flow of all the rivers and streams on the planet into the ocean. And that's almost certainly a lower limit because when you have low temperature circulation, it doesn't express itself very well in that heat flow signature. So it could be 2 orders of magnitude higher than this. We don't really know. Okay? But it's a big flow. And it's a big enough flow that it's as if the planet, the solid Earth, is breathing the ocean in and out, and every breath takes 500,000 years. So over the course of geologic time, the ocean has circulated in and out and in and out of the ocean crust. In addition, if you look at the porosity in the ocean crust and this flow rate, it means the fluid residence time in the crust is about the same as deep water in the North Pacific. Well, no wonder this is important for delivery of carbon and nutrients to support a subsea floor biosphere. You're recycling that fluid at a very high rate. In fact, if you take these flow rates into account, the water-rock ratio for ridge flank hydrothermal circulation is like 100 to 1,000 on the Earth, given the average age of the seafloor. So there's a lot of fluid and a lot of solutes, a lot of carbon that's being delivered into that subsea floor environment, much of it at low temperature. So here's a permeocentric view of the universe. The things that we care about, the things we really want to understand, are often in the box over here, but we can't measure them directly. And the things we can measure most easily are sort of the states of our world, the mechanical state, the thermal state. Well, if you want to take these and interpret these processes, you have to go through permeability to do it. You have to decide whether you think it's a porous medium, or it's a fractured medium, or it's a fractured porous medium, and what are the shapes of the fractures, and how widely spaced are they, and how many of them are there? We need to know that in order to make these conceptual leaps, because we can't measure these things directly. So what do we know about permeability in the ocean crust? Well, we know something. This is a compilation of every measurement that's been made in a borehole in the last 40 years. It's at 13 sites. That's how many have been measured. This is permeability on a log scale. This is low permeability here. This would be like a fine clay or a liner on a landfill. This is 1 Darcy. That's a good oil reservoir or a good groundwater aquifer. And this is 100 Darcy, so that's pretty high permeability. And this is depth into volcanic rock. So forget the sediment for the moment. And most of the data is from sites that are 8 million years old or younger. The oldest seafloor is 160, 170 million years old. So we don't have a lot of data for sort of older seafloor sites. There is some consistency. We have about a 4 order of magnitude range in the uppermost ocean crust. Most of the high values are in small intervals. We only have data from 2 deep holes, but they show low values. So from what we know, most of the permeability is in that upper some hundreds of meters. It probably does vary a little bit by spreading rate, but we do not have that nailed down in a significant way. So it's permeable, and that's what allows all that water to move through. But there's a problem. The problem is that much of the seafloor is covered by much lower permeability sediment. And these plots show for the Atlantic and the Pacific, as a function of seafloor age, the typical sediment thickness. For much of the seafloor, there is 10 or 20 or 30 or 100 meters of sediment. And the reason that matters is because the sediment has a much lower permeability than the basement, typically 2 to 3 to 4 orders of magnitude less permeability than the volcanic rocks of the upper ocean crust. This diagram shows what flow rate you need to extract lithospherically significant amounts of heat with flowing water. And given these typical permeabilities for marine sediments, these curves show the flow rates that would actually occur as a function of sediment thickness. And for virtually any rate beyond 10 meters of sediment, you cannot extract heat. You cannot get water to flow through marine sediments fast enough to extract heat. So to wrap up this introduction, we have 3 inferences and 2 questions. There are large flows of water moving in and out of the seafloor, and they're sucking out a lot of heat and moving solutes around. Much of that occurs at low temperature on ridge flanks, and the volcanic ocean crust is permeable. But how does the water get in and get out, and what actually drives that flow? Seamounts to the rescue. Right? It turns out that the seafloor is dotted with thousands of seamounts. The estimate used to be millions. Now it's been lowered a little bit on the order of maybe 100,000, but they're all over the planet. These are just the ones that have been mapped by satellite, primarily. And one interesting characteristic of that is that unless the radius is greater than about 3.5 kilometers, you cannot see them with a satellite. So the global census is actually based on a size distribution from satellite data, and then it's bootstrapped with ship crossing data and extrapolated to smaller sizes. Okay? But still, there's a lot of seamounts out there, and so they provide these pathways. And now I'm going to, in the meat of the talk, I'm going to give you two field examples of where we have these basement edifices sticking up through the sediment and how they influence this hydrothermal circulation in the seafloor. The first site is offshore of North America. We're going to go out here into Cascadia Basin, and the site we're going to look at is right here. This is the depth, and you'll see it's pretty even here. And the reason this is all the same color blue is that during Pleistocene sea level low stands, when the sea level was lower, all these big rivers, the Columbia, the Fraser, they dumped enormous amounts of sediment into Cascadia Basin and filled it in at a young age. So we have kind of a flat seafloor, lots of sediment, and a few seamounts poking up through that sediment. So we'll zoom in on that box. Now we have swath map data. So this is sort of resolution of 100 meter pixels, give or take. Right? Regional sediment thickness is like, call it 500 meters. Only a few outcrops. A big one down here we call Grizzly Bear. 3 small outcrops that were found earlier, and the oceanographers involved, because they were 3 different sizes, they called them the 3 bears, B-A-R-E for Bear Rock. The biggest was Papa Bear, then Mama, and Baby Bear. You can't even see it here. It's inside that gold circle. It's about the size of a football field. One other outcrop here that was found with swath mapping. These are all sites of hydrothermal discharge, and Baby Bear is the best studied. The total flow of fluid from that outcrop is about 10 liters a second. And it's enough with the fluid coming out at 25 C to be equivalent to about 1 to 2 megawatts, the same as one high temperature vent. So this is Baby Bear outcrop, a feature the size of a football field, weeping low temperature hydrothermal fluid with the power output of a vent. Okay? So we think that water actually flows in here and then flows to the north. Why do we think that? Well, here's a blow-up of Baby Bear and Grizzly Bear. Note the different scale bars, the horizontal scale. The red dots are heat flux measurements, and the black dots are seismic profiles using sound to image the subsurface at the bottom of the ocean. Now we'll take a look at 2 crossings for these seamounts. Here's Baby Bear, here's Grizzly Bear. You can see Baby Bear is tiny at the surface, but most of the edifice is buried beneath sediment. These are now shown at the same scale. Grizzly Bear is much taller, sticks up about 650 meters. Here are the heat flow measurements made as you approach Baby Bear, characteristic of the venting. The heat flow is swept up as you approach a seamount. It's a conductive signal of this hose of warm water shooting out through the top of the seamount. And in fact, this is 1 watt per meter squared, but the highest measurements on top of Baby Bear are 60 watts per square meter. Okay? A lot of heat focused out through this very small feature. In contrast, near Grizzly Bear, we have these little heat flow moats as 2-degree bottom water gets sucked in, and it suppresses the isotherms. So we actually have heat flow cut in half as you approach the edge of that outcrop. We also have chemical evidence, and there's a number of elements that have been used as tracers, as well as isotopic measurements. Here's just 2 strontium isotopes and sulfate concentrations going from south to north, from Grizzly Bear to Baby Bear and to the north. And this shows something that you see typically in groundwater systems. The longer the water spends in contact with the aquifer, the more the water looks like the aquifer chemically. And as you go from south to north, the water becomes increasingly chemically like the rock. So that's an indication that there's dominantly flow here from the south to the north. What drives it? Well, what makes the water flow is a hydrothermal siphon. And the concept is that in a place where you have recharge, you have a cold column of water that's got low temperature to depth because these temperatures are suppressed by the recharge, and that gives you a relatively dense fluid. At the discharge site, you have a warm column of water coming out, and that gives you this concave up profile with higher temperatures and therefore higher densities. And if you just bootstrap down to the bottom of the column and calculate the pressure here and here, you've got more pressure at the bottom of the cold column than you do at the bottom of the warm column. And if there's a connection, the siphon will run. So what kind of pressure can this generate? Well, if you put your hand in front of your face and blow hard, that's how much, about 1 atmosphere. And these outcrops, in the case of the Juan de Fuca flank, are 52 kilometers apart. So this pressure is pushing water 52 kilometers through the upper oceanic crust. And a couple of years ago, we finally fulfilled a dream I've had for a long time to model this in 3D and actually make it work, show that it's physically workable and it can be sustained. This is work that Dustin Winslow did as part of his PhD thesis. So we built a big grid. We've got geometrically correct but idealized grizzly bear and baby bear. We heat the system from below. And I'm just going to show you a quarter section through here. Here's water recharging at grizzly bear, mixing. Some comes back out. We actually see that in the field. A fraction of the water heads to the north. Baby bear is only a site of discharge. In fact, this system favors discharge through the smaller outcrop, and we start the models the other way. They flip spontaneously in the first couple of time steps. These systems are discharge dominated. That's a phrase that Joe Can developed years ago in describing ridge crust hydrothermal systems, that counterintuitively, the water tends to come out where it's harder to come out. It goes along a path where recharge wants an easier path, discharge takes a harder path. And that does seem to apply in this case. We were also able, with the heat flow that the model predicts, to constrain the thickness of the basement aquifer and the permeability within about an order of magnitude. And it turns out this range of permeabilities is exactly what we've measured in the field in boreholes at these sites. And they're significantly lower than what we predicted with 2D models, and they're much lower still than what are predicted with tidal models. And this illustrates one of our challenges in ocean crustal hydrogeology is we have to model these things in all of their glorious complexity to get the numbers right. If you simplify too much, then we're missing part of the physics. This just shows the pattern of fluid flow. In this case, I stripped off the sediment and the aquifer, and I've got the vectors just sort of floating in space. I zeroed out the Z just for graphical purposes, and I'm only plotting 3% of the vectors so you can see them. Otherwise, it looks like a pile of straw, and you can't even see what's going on, and it's a dipole. You basically have water flowing like this, and you have water flowing around like that, so you can get retrograde motion behind baby bear and grizzly bear. Again, you can see a complex recharge-discharge pattern at grizzly bear, only discharge at baby bear. All right, so this is the first place we've actually figured out how this works, and it turns out it's an exception. This site is anomalously not anomalous, or anomalously normal, except it's not normal because most of the world is down here. We are essentially at lithospheric heat flux for this site. That 1 or 2 megawatts coming out at baby bear, it's such a small amount of heat that it has no influence on the regional heat flux pattern. There's no deficit. Okay? The next example is from the opposite. It's a place of about 20 million year old seafloor where we have extremely efficient heat flow suppression because of very rapid fluid flow. And that's located here on the Cocos Plate on the edge of the Middle America Trench. We're going to zoom in on this area. There was a series of surveys, heat flow measurements shown here. The purple and blue is cold. We identified an area the size of Connecticut where about 60 to 90% of the heat is missing. So much more efficient, right? Big heat flow deficit. The total deficit here is about 1 gigawatt for this area, and only 11 outcrops. Okay, so only 11 places that are not covered by sediment where that water could get in and out. And 2 in particular were of interest. This pair of outcrops here, Tengo and Dorado. If we zoom in on those, here was the swath map from that original survey. They're about 15 kilometers apart edge to edge, 20 kilometers apart or so center to center. Tengo is a monster. It's about 4 times the size of grizzly bear, quite a large feature. Here's the map we had from that swath survey, 50 to 100 meter resolution. We were able to go back and map with Sentry, which is an AUV. Now here's a 1 meter scale resolution map. This was just a reminder about how important high resolution mapping is, but how challenging it is to do remotely. Okay? And even this earlier map wouldn't show up. This feature does not show up on the satellite maps at all. It's too small. Okay? And yet, we hypothesized and then found it was a site of hydrothermal discharge. So here's Dorado, and then here's a seismic line. We're going to look at that seismic line across there. The heat flow is shown here. Hot colors on the outcrop, cold colors on the side. Again, a lot like baby bear. The heat flow didn't show up too well, but here are the heat flow values skyrocketing. We made measurements on top of Dorado of greater than 10 watts per square meter. And here are the isotherms swept upward, characteristic of warm fluid coming out. But this fluid is about 10 to 15 C. Okay, so much cooler than the water that was reacting below Baby Bear. That area is more like 65 degrees C. So we went out and looked for that discharge, thinking there must be a fire hose. In fact, our analytical calculations was maybe they ought to be like 1,000 liters a second coming out. Not 10, but 1,000. And that would help explain why it's so cool. And here's what was actually found. When it was found, it took over a week. When you get close enough, you actually get the refraction effect, the shimmering of 10 to 12 degree water coming out. And we learned to look for the albino crabs, the octopus, albino shrimp, these little worms. And we found the water coming out kind of along these walls. And collected, this is one of Jeff Wheat's tools, the first samples ever collected of this low temperature hydrothermal end member coming out through the seafloor. People have looked for sites like this for decades and not found them because they're hard to find. You know, even above a high temperature event, the temperature anomaly in the water column might only be, 10 milli-K if you're 100 meters off bottom. These are small signals. The water had about half the dissolved oxygen of bottom water, the stuff that was coming out. Most of the major ions looked very similar to bottom water because it's reacting at low temperature and it has a very short residence time in basement. Some of the trace elements, the metals, had demonstrably different chemistry. Okay, so they can have an effect on a global basis, even though the difference in chemistry is small because the flows are so big. Right? Was it a fire hose? Well, kind of, but it was probably more like this, where these are the shrimp and the crabs and things. So the water is coming up from depth, but then it's spreading and being sort of diffused out through Dorado outcrop. And then recently we have a paper, we just got reviews on Friday. They were pretty good, so hopefully we'll get this turned around quickly. We've modeled this system. This is work by Rachel Lauer, who was a postdoc at UC Santa Cruz. Kind of similar to the earlier models, but this time 2 outcrops at the corners, a small one, a big one. And these diagrams show seafloor heat flow maps, what the heat flow would be based on fluid flowing into one outcrop and out through another with basement permeability of 10 to the minus 11, 10 to the minus 10, 10 to the minus 9. That's 1,000 Darcys. The band here is the observed heat flow in that region, and the blue is the model result. So the way that we match the heat flow with the model is with 1,000 Darcys of permeability in basement, 1,000 times higher than around that North Pacific site. Kind of makes sense. You want to drive this with a hydrothermal siphon. It turns out the pressure difference here between this outcrop and that outcrop, put your hand in front of your face and blow gently. That's the driving force. Okay? It's about 1/10 of an atmosphere. And to get the flow rate, to get the heat flow to match, we end up predicting with our models 1,000 to 8,000 liters a second through Dorado outcrop. So on the order of, call it 100 to 1,000 times Baby Bear. All right, so to wrap up this sort of quick overview, we have a huge variety of hydrothermal styles on Earth. We've got different heat sources, from essentially magmatically linked to exothermic, maybe some residual sensible heat from cooling of the crust, to these lithospheric driven systems. I haven't even touched on a bunch of factors that are probably important just because we don't have time, but we also have bathymetric effects in tides. Why does bathymetry matter? Well, you know that Rayleigh number calculation that we all learn, where you calculate the permeability to get convection to occur? If you take an aquifer and you tip it by a degree or two, it's unconditionally unstable. If you take an aquifer and you add heat on the side, it's unconditionally unstable. The critical Rayleigh number is 0. They all convect. Right? I mean, really the question is, why isn't there more convection? And it's probably because of the sediment. It's probably because of blocking off of those pathways. But it doesn't mean there's not circulation within the rock itself. And bathymetry can be important both in terms of creating these chimneys or pathways, but also, again, because it creates a boundary instability, which can generate convection. On the Earth, our advective heat loss is on the order of 1/4, okay, of the total budget. What's it going to be on an ocean world? Is it going to be more because there's no sediment, or maybe there is sediment? Maybe there are hydrothermal particles that are going to help to create the same kind of geometry that we have on Earth. Part of what makes hydrothermal circulation so vigorous on Earth is the heterogeneity. The fact that there are some parts of the rock that are more permeable than others. If it were all the same, if it really were just a porous sponge, and there were no gaps, all we'd have are these little shallow low temperature systems. The world wouldn't look like it does. The reason we get these reaction zones and then these narrow chimneys is because there must be a seal. And it's either going to be a lack of cracks, or it's going to be diagenetic, or it's going to be both. But you do not get the focusing of flow without seals, and then without openings through those seals. And I think that applies both to low temperature ridge flanks and probably also to higher temperature systems. On Earth, we've shown fluids can travel tens of kilometers, maybe hundreds. Part of that heat flow deficit off Costa Rica potentially is explained where basement rocks are exposed on the outer trench bulge off Nicaragua. That survey has been proposed and hasn't been run. That's hundreds of kilometers away. Do the fluids move that far? We don't know. Okay, but they can move at least 50 kilometers, if not more, as long as the permeability is high enough. And the driving forces don't need to be big in order to get a lot of water moving. You can have subtle differences in heating, in properties, in topography, and then you have the mechanical effects of the tides themselves. People talk about fault valve pumping on Earth. I'm skeptical it happens much on Earth, but on a tidal system that's flexing, you bet. I mean, you could have mechanical pumping of water in addition to the hydrothermal effects. We don't know anything about how those interact. All right, so how does all this apply to ocean worlds? So here was just kind of a brain dump of some questions, really. And maybe we'll learn about some of this at the rest of the meeting this week. What is the distribution of reaction, discharge temperatures on ocean worlds, right? I mean, I think a lot of us work with one kind of hydrothermal system, and we think of that when we think of a hydrothermal system. But I've tried to emphasize on Earth, it's a diversity of hydrothermal systems. And what about for fluids other than pure water? And are we in a range where we can have phase separation? That's a big controller on the chemistry events on Earth. But are we in the right pressure, temperature, chemistry regime in ocean worlds that we could actually get multiple phases? On the Earth, our systems, both on ridges and flanks, are discharge dominated. That is that the flows tend to come out where the water seems to have to struggle a little bit to get out. Do we have heterogeneity on ocean worlds? I would guess yes, but I have no idea what it looks like. Right? And are there sediments or reactions which then help to form seals? And I think that's probably necessary to get the vent forcing if it occurs in the ocean. The plumes that are coming out through the ice, of course, they are coming through seals. The ice is the seal, and they're coming through the cracks. What's the influence of lower gravity on things like the driving forces? Can you maintain a low temperature system if you reduce gravity by a factor of 10? Because now you've reduced the influence of that pressure difference. Well, that's going to create different physical relationships. And particularly if the system is constantly being perturbed by tides, can you make a siphon with low gravity? I don't know. That would be a fun thing probably to model. And then what role does topography play? And in this case, we have topography maybe not only at the water-rock interface, but topography at the water-ice interface as well. And that may have an effect potentially on that circulation. Again, we need to figure out what the impact of that tidal forcing might be. We do see effects on Earth. There have been many studies that have shown you can see a tidal influence on both the temperature and the flow rate of hydrothermal systems, both at high temperatures and at low temperatures, but we don't fully understand how that works. And of course, the exothermic reactions could be quite important if you have a lot of ultramafic rock that's exposed. And I think for me, the big one is, can we answer any of these questions without sending landers down through the ice and making direct measurements? Because a lot of these issues come down to small scales. And I'm not sure yet how we can answer these questions without actually getting into the ocean. So with that, I want to acknowledge just a lot of people who contributed to these and other studies. And of course, the folks who support us at sea and the expedition-based work, and then the funding agencies who have helped us out over the years. So I'm happy to answer questions. Thanks.
All right, questions for Andy?
Maybe you said it and I just missed it, but when the modeling you did, how do you initiate it? Do you kind of get the flow started, or how do you initiate the model?
Yeah, so I didn't talk much about the program itself. It's a transient model. And so you just need to establish an initial condition. And for the different models, we've tried them different ways. We'll try a cold hydrostat, an ambient hydrostat. In some cases, we give them what's called a gentle push. We'll create a column that's cold or warm, and then start it with that. We did that specifically to experiment with when they would flip.
Okay.
And in general, the results that I showed you occur in all cases of initial conditions that we've tested. And the systems will sustain themselves infinitely, essentially. So we don't actually model a true geological initial condition, because that would require modeling crustal construction and sedimentation and things like that.
And then underneath there was no heterogeneity in the
Only
the
layering.
porosity.
Yeah, right.
Yeah.
So we haven't even gotten to the point of introducing pockets of higher or lower permeability. I took out 8 slides on faults this morning because there wasn't really time. But we've got a master's student just did a hydrothermal modeling study of fault systems, and we see big effects there. They're not in those models that I showed you. It's a separate set of problems. Yeah.
Mark Yorso one time joked that if it wasn't for the ridges, the seafloors would have towers of brucite, right? Because this is recycling the magnitude, sequestering a lot of magnesium. Yet we find, Lost City is towers of brucite. We find top pillars in the Cayman. I guess what I'm alluding to is how well do we understand the chemical coupling to the system?
Oh.
We talk about heat and flow,
Right.
but we don't really know the chemistry variability.
No, that's right. I mean, I think where we're most confident is in box modeling of reaction, right? You mix certain phases together, give them conditions, see what you get. The challenge with a fully, three-dimensional heterogeneous representation is that all of these functional relationships, say between infilling of a crack and its properties, are completely ad hoc and unconstrained. So we know a lot from, outstanding experimental and theoretical work that shows when you mix a batch of this with a batch of that, what are you going to get and how long does it take? I mean, there's work to do, but that stuff is, pretty solid. But once we try to couple, once you try to couple in complicated flows, you've just got so many decisions to make. And we don't have the data. That's the fundamental limitation. The modeling is not limited by the codes. And it's not limited by the computers. It's limited by the data.
Just by the way, the previous question, tomorrow my talk might address some of that. Just out of curiosity, for your simulations, what are your boundary conditions, especially for the one where you have the 2 seamounts at the corners?
Yeah, so for the question is about the boundary conditions. For the one where so for all of those simulations, we use no flow side boundaries. We've done some testing with a hydrostatic side boundary, and it depends. Depends on the simulation. But they're in the first case, we're really looking at the dipole, and that's in a location where there aren't many outcrops, so that's pretty well justified. In the second case, as we show in the paper, this is based on a field of outcrops analogy. And if you assume symmetry, then those outcrops each represent a quarter of an actual outcrop. So what that represents is a quarter of a field of outcrops that goes to infinity. So the challenge with hydrogeologic modeling is one of scale. The processes are occurring through cracks and faults and small features that are millimeter scale or smaller, and we're modeling systems that are up to 130 kilometers on a side. And we need to finish the models in a 4-year dissertation. And so, there are just limitations. If you could fire these things up and let them run for years, you could model this at, whatever scale you want. In the case of the Dorado area, this was the first set of models at those very high permeabilities. The high permeabilities result in fast flow, which requires small time steps. It's just the physics. So, we'll probably need to do some creative thinking, but the next step there is to build out, to put in more outcrops at a kind of a distribution that looks a little bit more like the field. But I think to a zero order, that's the process. There are certainly, idealizations.
Yeah, and you mentioned the importance of sediments in creating seals and I guess defining flow paths and maybe also forcing flow deeper and so warmer. If you don't have sediments and maybe that's sort of a good first order idea for some of these oceans, does it mean that advective flow sort of collapses onto the very high temperature discharge, or does the potential for mechanical forcing distribute it more broadly but much more with a much smaller delta T?
Great question. I mean, we know at mid-ocean ridges where we have a nice big heat source and we don't have sediment, we have vigorous hydrothermal activity. Okay, so it certainly doesn't prevent it from occurring. But it does tend to result in it happening in a few locations. That's also just a function of the heat balance. There's only so much heat coming in along with the magma. So you can't support high temperature venting continuously along mid-ocean ridges, even at fast spreading ridges. It's just a heat balance issue there. But I would wager that you might lose some of that low temperature end, which is small in terms of chemical differences, but big in terms of the flows, big in terms of the water rock ratios, big in terms of delivering things to bugs that might be living in the rock. So it's a great question. I mean, I think you could certainly have activity, and especially if it's driven exothermically. But maybe it's not so much the distribution we have on Earth.
But you were saying both topography and faults could also
Absolutely.
those things as well?
Yeah, absolutely. And in a system that's being flexed and shattered frequently, you can well imagine heterogeneous pathways being opened and closed on some time scale, and those providing the opportunity for higher temperature discharge to occur. But we haven't done the physics of that yet, right? So that would be a great. I mean, there's so many things to explore. You take an ocean world that's Earth, and then start plucking or substituting, elements that would make it more like an ocean world in Enceladus or Europa or someplace else, and it'll be interesting to see how much it matters.
One last one.
Yeah, as a benthic biologist, this is really fascinating. I've been reading this about some years, but I'm trying to understand, because this is so important for the biology, not just the subsurface microbes, but for life on the seafloor that'll be controlled by the distribution of this activity, controlling the biogeography and biodiversity of life on Earth in the deep ocean. So my question really is, I understand the flanks and the diffuse flow on the flanks of mid-ocean ridges and seamounts that are located proximal to mid-ocean ridges, but what about the mid-plate beyond hotspots when things are cold, when things are getting towards subduction zones, for example? I'm thinking of the Phoenix Islands. I go out there and look all the time for hydrothermal activity. I don't see a lot, but when I go to the Western Pacific and go to those seamounts, it's dramatically different fauna from seamount to seamount based on the chemistry, for sure. But I think that's a lot to do with the temporal variability of what you're talking about as well.
That could be.
So I'm really curious about what the seamounts are like, what their role they're playing in sort of a mid-plate region.
Yeah, it's a great question, and we don't know. The only two that have been studied in detail are the two I talked about, and that's out of maybe 10 to the fifth. So I think we have a lot of work to do on seamounts to try to understand. I mean, and what's interesting to me is a lot of these issues are non-intuitive. You think, oh, it ought to be like this, and then we go out and it's like, no, it's actually something completely different. So like finding in that picture you saw the octopus that are on Dorado, and there was a paper that just came out that Jeff's a co-author on. It got a lot of press a few weeks ago. That was a completely, none of us went out there to say, and we're going to find octopus, and it'll be this isolated population, which is, doomed, somehow because they're all there by themselves. So I think through this exploration process and through the modeling and through the thermodynamic calculations and through the batch experiments, through all of this, we're going to start to really learn more about how these pieces operate and then just need to put those together. So I don't know the answer to that specific question. But I suspect it is important. The different seamounts have got different chemistry, different geologic history, different alteration history, and I would certainly expect that to have an impact on the biology.